Today we will be discussing the physics of the violin.
We are going to start off the video by defining some terms related to the tension of the physics string. To define simple harmonic motion, it is the oscillatory motion where the net force on the system is the restoring force which is proportional to the displacement from equilibrium. This relates to the violin, as the bow makes contact with the string, the vibration of the strings creates sound waves, resulting in the oscillations of the violin string. That is where simple harmonic motion comes in. These vibrations created from the contact with the taut string are producing fundamental sinusoidal frequency.
This equation represents Hooke's law. The negative sign causes the force to restore because it flips the sign of the force. The K is the constant which is proportional to the displacement. Because of this, as the displacement increases, the restoring force increases.
Next, we'd like to talk about standing waves. Standing waves are defined as individual points on the string that oscillate up and down, but the wave itself does not travel. When plucking the violin, a disturbance is generated which creates standing waves in the string. The standing waves in the violin strings produce the stable, controlled vibration and create the sound the violin ultimately makes. This is an example of a standing wave diagram. As you can see, the reflected pulse is inverted, but the amplitude is unchanged.
Fundamental frequency is the lowest frequency that produces a standing wave. And in terms of the violin, the sound that we hear is determined by the fundamental frequency that varies by the notes. And as shown in this diagram, by different instruments as well.
Hey guys, in this upcoming video, we're going to solve for the tension in the A string of the violin. First we're going to derive the equation, and then we're going to go from there.
We know that velocity is equal to the square root of force of tension over linear mass density. We also know that velocity is equal to the wavelength times its frequency. We can plug in velocity for the wavelength times frequency and set it equal to the square root of force of tension over the linear mass density. Solving for force of tension, we get wavelength squared is equal to times frequency squared is equal to the force of tension over the linear mass density. Then you can move the linear mass density over by multiplying it, and you get force of tension is equal to the wavelength squared times the frequency squared times the linear mass density. And we also know that the wavelength is equal to 2L. So, plugging in wavelength, we have force of tension is equal to 2L squared times frequency squared times the linear mass density. And this will be the physics equation for our project. We know that the length of our violin string is 0.325 meters, so we are able to plug that in for the 2L, which signifies the wavelength. We also know that for an A string in a violin, the frequency is 440 hertz, and we found that the linear mass density of our string was 0.006 kilograms per meters. Solving for the tension for this, we have 53.8 newtons.
When a string is excited by the bow, it creates a standing wave. This standing wave oscillates at a certain frequency. It is this frequency which is amplified by the body of the violin, which we hear as its sound.
This graph shows the square root of tension versus frequency. From our equation, we have on the y-axis is tension and on the x-axis is frequency. We decided to look at all four strings to show you the relationship of the square root of tension versus frequency. The thicker, more massive strings vibrate slower. The thickness increases from strings E to A to D to G. Even though the length of the string does not change, the tension will increase accordingly to the frequency. The two have a proportional relationship. As you can tell from the graph, the G string has a frequency of 196 Hz, making it the lowest frequency and the lowest square root of tension, also creating the lowest pitch. Because of the proportional relationship as you move on, the D string has a frequency of 293.7 Hz, and the A string has a frequency of 440 Hz, and finally, the E string has a frequency of 659.3 Hz, making it the highest pitch of the strings.
So we just wanted to talk about the three topics that we discussed at the beginning of the video and analyze how they affect the violin and strings.
So in terms of standing waves, the standing wave is affected by a change in wavelength, such as moving your finger closer or farther from the actual point where the bow touches the strings, which results in a change in frequency and tension.
Simple harmonic motion affects the violin strings by affecting and altering the oscillations and vibrations of each string.
And lastly, fundamental frequency affects the pitch of the string. For example, the G string has the lowest pitch and as well as the lowest tension and the lowest fundamental frequency, so that relationship is very clear. So we hope you guys learned something today. Thanks for watching. See you next time.